Hello all and welcome to my presentation. Today I'll be talking about my research project, which is about rethinking the feasibility of performing anonymous voice calls using the Tor network. I am Piyush Kumar Sharma, and this work has been done in collaboration with some wonderful colleagues, namely Shashwat, Nikhil, Mukulika and Sambuddha. Anonymous calls in general have wide applicability, ranging from normal users who just don't want any eavesdropper in the network to know if they are talking or to whom they are talking, to some specific use cases such as those of covert journalists, informants who want have some information but don't want to reveal their identity, to whistleblowers and so on. Unfortunately, there is no functional anonymous VoIP calling system as of yet. One way to proceed about this problem is to build a completely new system from scratch. It will have its own challenges, which are recruitment of users and scalability requirement of the users, the bandwidth requirement, and so on. An alternative approach is to use already existing popular anonymity systems, on top of which we can try to send the VoIP traffic. On that note, we know that Tor is one of the most popular low latency anonymity system. It has about 2 billion daily users and it serves about 450 Gbps of bandwidth to its users. And let's not forget the amount of effort it took the researchers in the past decades to bring Tor where it is. Uh, Despite its good applicability to general applications of anonymity, such as web browsing, Tor is believed to be unsuitable to perform real-time applications, to support real-time applications such as VoIP. There are some inherent reasons for that. One is that VoIP packets are generally UDP. However, Tor only supports TCP packets. Secondly, there are multiple relays through which the Tor's packets traverse, and because of that, some delays can be introduced. This belief has also been validated by a few measurement studies, which started back in 2013, where Rizal had a very unique idea where he tried to tunnel the VPN traffic using a VPN. However, there was a shortcoming that the Rizal study considered relays only in the European Union. They did not consider the perceptual call quality. And second, there was a second study which was done by Husser et al. In 2017. It consisted of performing 100 calls over the real Tor network. However, the conclusion which both the studies draw from their analysis was that Tor was unsuitable to support anonymous voice calls. This brings us to the motivation of this study. As we can see that the amount of calls that were performed and the way the analysis was done, the complete comprehensive picture of the call quality ecosystem over Tor is not very clear. More specifically, in this study, we aim to study the impact of different network parameters such as RTT and bandwidth and how they affect the call quality. If we are to talk about the Tor network, we really need to cover a lot of Tor relays in order to be sufficiently confident about telling about the performance of the complete Tor network. Thirdly, we were very interested in gauging the actual human perceivable call quality, as we can measure the network parameters for measuring quality, but at the end of the day it's the users who have to use the system, and thus perceptual quality becomes important. Moving ahead, we would like to introduce the metrics which we use to evaluate the call quality. The first metric is the PSQ metric. It is an international telecommunication union standard, with PSQ stands for perceptual evaluation of speech quality. It provides an objective score to measure the user perceived call quality, and this objective score has a very high correlation with the subjective score given the actual human subjects. This subjective score is also known as the mean opinion score. And secondly, we use the metric one-way delay. One-way delay basically tells about the lag when we are talking to someone, and this is also a metric which reflects the perceivable call quality. As for the exact values which we considered for terming a call as a good call, Uh, Following ITU guidelines, we considered that any call which has a PSQ score of above 3 and a one-way delay of below 400 milliseconds were considered as good quality calls. So we use this threshold throughout our study. Moving on, we now describe the setups which we used for performing our comprehensive study. As we all know that VoIP is general UDP and Tor transports TCP. There are broadly two ways to now send the VoIP traffic over the Tor network. One is to somehow tunnel the VoIP traffic over the Tor network, that is by using a tunneling medium such as a VPN, and the other way is to directly generate TCP packets from the VoIP application itself, so that these TCP packets can be directly transmitted to the Tor network. Corresponding to both these setups, both these approaches, we have two setups which I will be describing next. First setup is the vTOR setup. As you can see from the diagram that the client machine or the caller machine has the Tor utilities, VPN utilities, and any standard SIP calling utility installed in its system. It initially starts the Tor browsers such that it establishes a unique Tor circuit through 3 relays, eventually to the other end. Then the client runs the VPN utility. This VPN utility establishes a connection to the VPN server through the Tor network. And then finally, the client runs any standard SIP utility. Once this happens, the client generates SIP packets, as can be seen in the diagram marked as S. These packets are encapsulated inside the VPN header so that they can be tunneled through to the VPN server. Once these packets, this VPN packet is, once the SIP packet is tunneled inside a VPN packet, it is then transferred through to the Tor network, eventually to the other end, that is the VPN server. The VPN server decapsulates these packets, and these SIP packets are then forwarded to the SIP server, which manages the protocol using the standard SIP, which manages the caller and the callee using the standard SIP protocol. The second setup, the basic setting remains the same. That is, we have a client which has already established a Tor circuit through the Tor network. And in this case, the client runs a utility which actually directly generates VoIP packets in TCP, which is a mumble application. The client just runs this utility and forwards all its packets to the Tor SOCKS interface such that they are able to transmit over the Tor network. These packets then eventually reach the mumble server, which mediates the call between the caller and the callee. So this is about both our setups. I would like to mention that the results of both the setups were the same. So for describing the results which we have considered in the subsequent slides are for the vTOR setup. However, the mTOR setup results can also be referred to in the paper. So till now we have described the metrics we use, the setups we use, and now we would like to tell the general flow which we followed for performing the experiments. Since there were a lot of calls we needed to perform, we automated these calls. Secondly, as soon as the call was established through the Tor network, we played an audio file which contained human speech at the caller end. This call would traverse through to the Tor network and the VPN server, and then eventually reaching the callee. And then at the callee, this call was again recorded. The call was recorded in order to calculate the PSQ scores. Additionally, we also measured the network parameters such as the RTT and the available bandwidth. This brings us to the actual experiments. Pertaining to the previous studies, which performed a few hundred calls, in our pilot study, we also performed 1,000 calls, and surprisingly, we obtained good performance for more than 85% of the calls. That is, 85% of the calls obtained a PSQ score above 3 and a one-way delay of 400 milliseconds. However, one may argue that this performance might be an artifact of the network at that time. That is the reason we went ahead and performed a comprehensive study, and we devised various experiments to actually be confident about the call quality over the Tor network. So these experiments were broadly divided into two categories: the in-lab experiments and the internet experiments. In the in-lab experiments, we had the complete control over cross traffic. However, in internet experiments, we did not have any control. Moving on to the in-lab experiments, we used all the we used a private Tor network for performing these in-lab experiments. And this private Tor network was set up using actual physical machines. The purpose of the in-lab experiments was twofold. One was to analyze the overheads which were introduced because of the introduction of these new entities such as the VPN, the Tor, and the Mumble, and so on. Second intention was to study how the call would behave in the presence of varying cross traffic. That is, if we vary the cross traffic, how does the VoIP call behave? As for the results, you can see we can start by the table on the left. A direct SIP call requires a bandwidth of about 84 kilobits per second. However, as soon as we perform this call by establishing a VPN tunnel, you can see that the call quality was still good. However, it required a bandwidth of 108 kilobits per second pertaining to the additional headers which were added because of VPN. Similarly, in the third case where we transmitted this VPN tunnel over the Tor network, the bandwidth requirement increased to 120 kbps. So moving, the interesting finding is in the table on the right. As you can see, since we had control over the cross traffic, so we keep intentionally keeping the kept increasing the competing streams in the network over a 10 megabits per second link, as you can see in the first row. Initially, when the available bandwidth per stream was about 133 kilobits per second, you can see that the PSQ score was relatively high, which was 4.2, above 4.2. However, you can see that as soon as the available bandwidth per stream fall down a specific threshold, that is when the bandwidth was about 117 kilobits per second, you can see that the PSQ score fell dramatically and the call quality became poor. So overall, to summarize the in-lab experiments, we can say that for good call quality, we require a fixed bandwidth for its entire duration, and this fixed bandwidth is about 120 kilobits per second in case of VTOR, and even if there is a slight drop in the availability of bandwidth, then the call quality would be poor. Next, we moved on to the internet experiments. As we all know, if we have to make a claim about having good or bad performance over Tor, we would require a variety of experiments for that. Starting with the variation of Tor circuits, we created zero point 0.5, since we performed 0.5 million calls, we created approximately 0.5 million Tor circuits, which involved approximately 6,650 Tor relays. Secondly, we did not wanted our performance to be an artifact of a single client sitting in our institute. That is why we even varied the caller and callee locations throughout the globe across 7 countries. Similarly, we tested it for scenarios where either the caller wanted the anonymity or callee wanted the anonymity or both of them wanted the anonymity and so on. Similarly, there were other scenarios which we tried out for the internet experiments and whose results I'll be mentioning shortly. Lastly, we also performed a user study which involved about 20 participants. As you can see from the results that this is the results of one of the experiments which we performed. This contains a sample of 42,000. As you can see on the left, the CDF of the PSQ shows that about 90% of the calls obtained a PSQ of above 3 for this particular sample, and similarly about 90% of the calls obtained a one-way delay of less than 400 milliseconds. I would like to mention that moving from 2-hop circuits to 3-hop circuits or three and vice versa did not have much impact on the PSQ score. However, as intuitively expected, it did have an impact on the one-way delay offered with these circuits. Moving ahead, these are some additional results. We also performed some experiments over the apps which the clients commonly use. We send the Skype and Telegram traffic over Tor, and even then we observed that the 80% of the calls obtained good call quality. And similarly, when we varied the codec, we obtained good call quality for about 90% of the calls. So the overall results indicate that that we obtained good call quality for about 85% of our total, that is 0.5 million voice calls performed over the real Tor network over the internet. Next, we did not stop here. We also performed a user study. PSQ scores can be measured for only call duration of about 30 seconds. Thus, we went ahead and performed a user study for calls above a duration of 30 seconds. 20 participants were divided into 5 random groups, and they were each given a file of 30 seconds, 2 minutes, and 4 minutes. The users needed to rate the call from a score between 1 to 5, and their rating was eventually recorded. We compiled these results, and as you can see in the table on the right, that all the groups prescribed a score of greater than or equal to 3 for all the recorded calls which we showed them. This further strengthens the claim about obtaining good call quality over the Tor network in majority of the cases. As for the reasons why we obtain good call quality, we have some insights. We already established in the control network setting that VoIP calls require a relatively low bit rate, which is about 120 kilobits per second. However, since we also measured the available bandwidth in these Tor circuits, as you can see from the diagram on the right, we obtained about 90% in about 90% of the Tor circuits. We obtained surplus bandwidth, that is a bandwidth of above 1 Mbps. So this clearly indicates that the contention for the VoIP traffic was relatively low throughout our study and throughout the Tor network. Alternatively, I can say the same thing in a different way. That is, we know that the PSP score is very sensitive to distortions in audio. If the bandwidth goes down below 120 kilobits, the PSQ falls down to below 3. However, we observe good quality calls in majority of the cases. This clearly indicates that the calls obtained sufficient call bandwidth for their entire call duration. And this overall suggests that the Tor currently supports a natural ecosystem for supporting VoIP calls. As for the consistency of our findings, since this was a longitudinal study, we also plotted a graph wherein we highlight the performance which we obtained in the different months of our study. Since the study was 1 year long, we have a box plot for each month, and as you can see that the overall performance does not vary much. Overall, to compare with all the existing literature in anonymous calling, which started off in 2010 with DRAC, where they gave an analytical model about how can we achieve anonymous calls, to Rizal, who for the first time conducted study. However, there was some biasness in the relay selection, to Torphone, which was available sometime in 2013. And however, it offered a very high one-way delay of 2 to 4 seconds, which was practically infeasible. Then we had Herd, which did not did any evaluation over the Tor network. However, it proposed a new system similar to Phonian, which also proposed a new system and said that the anonymous VoIP calls are not possible. To finally our study, where we established that currently the Tor network is a natural ecosystem for supporting anonymous voice calls. And this involved conducting experiments to a large extent with 0.5 million calls covering 6,650 Tor relays. Overall, to conclude, there is no anonymous calling system as of yet, which is functional, which is the reason we went ahead and tried to see if we can use the existing anonymity system, which is Tor, to perform these anonymous VoIP calls. Thus, we conducted a comprehensive measurement study, which included performing a 0.5 million calls over the Tor network, span across a duration of 12 months. Surprisingly, we observed call quality of we observed good call quality in a majority of the cases, that is 85% of the cases, and we believe that the good performance was basically due to the low bitrate requirement of VoIP calls and the surplus available bandwidth which is there currently in the existing Tor relays. Thank you so much for your time. I end with this and I'm open to questions now.